Okay. I apologize for not hitting the record button last time. Again, the technology is new to me too, but we are now recording today. So in future classes, if you don't get a message or you don't, I think everybody hears this meeting is being recorded. Want to hit the record button? Is that true? Okay. If you don't,
Yeah, we all hear.
yeah, please.
Yeah, I heard it go off.
Hey, Vile, hit the record button. So. All right, so I am going to put PowerPoint up here and share my screen. Actually, you know what? I'm going to try something different. No, I'm not. I'll do this. Share my screen. PowerPoint. Okay. Yes. Yes. Okay. So just to kind of very briefly recap what we did last time. 3 different forms of communication. Simplex, there's one transmitter, one receiver. Full duplex is transmitter and receiver on both sides. Information can travel both directions at once. Half duplex is information can travel from one side to the other, either being received or transmitted, but it can only travel in one direction at a time. Half duplex is walkie-talkies. Full duplex would be a phone conversation. Simplex would be, I think the example I gave is, I have a thermometer in the water that transmits every 10 or 20 minutes to a receiver in the house. That would be simplex communication. Okay. If I transmit characters serially and asynchronously, which is the only only mechanism that we're going to be looking at with a UART, even though there are lots of other modes it can be used in. Normally it will idle in a 1 state. A start bit is always a 0. There are then anywhere between 5 and 9 data bits, depending on how you set this up. There's a couple of 3 bits that actually set how many bits you are transmitting. There is an optional parity bit that is set to a 1 or a 0, such that if you're doing odd parity, there are always an odd number of bits which are going to be 1. If you're doing even parity, there's always an even number of bits which are 1. There is a check that can be enabled on the receiving side if the parity is off. If you don't always have an odd number of bits in a character that are 1 or an even number of bits, depending on even or odd parity, it will raise a flag, and you can process that as an error. A character will always end with at least 1 stop bit. There is an option for 2 stop bits as well. From the start bit to the stop bit or bits is called a frame. And then it will either, after that character is transmitted, it will either idle as a high, or there will immediately be another start bit. So depending on how fast data is coming. The time of 1 bit is a bit time, or the reciprocal of that is known as the baud rate. And common baud rates, I'll just, in RS-232, but I repeat this because if you're doing design project a couple of years from now, and you're connecting real RS-232 stuff, you want to be very careful. Logical 1 in TTL is represented by 5 volts. In RS-232, it's -3 to -25. 0 is represented by +3 to +25. That was a convention created long before TTL logic was created. If you put negative voltage directly into your 328, even as little as -0.5 volt, you have probably just toasted it. So you do not want to connect RS-232 levels directly to TTL. There is some standard connections that we talked about last time. Then there are chips, such as a MAX 232. There's also a 75, 188, 189, that are specifically designed to change TTL levels. Let me put a pointer on here. Specifically designed to take a TTL level 0 volts or 5 volts, and change it into a plus 12 or a minus 12. Right, and that can be interfaced. There's also chips such as a CH340, which you have on your board, that are designed to take RS-232 information and convert it into USB, which is short for Universal Serial Bus information. On our 328, there are 2 pins, and they are D0 and D1, that are receive and transmit, designed to emulate RS-232, not voltage levels, but bitwise. They are fed directly to this CH340 chip on the board, which connects to the USB on your computer. So you can serially transmit characters to your computer, and we're going to write a program to do that in just a couple of minutes. All right. I think we kind of left off there. There are 5 registers. Just like with the timers, there's an A and a B, and occasionally a C control and status register. The same thing is true on the UART. There is a data register where characters are received or transmitted. And there is a 16-bit baud rate register where I put a delay factor in to control the baud rate. 2 UARTs on the 328, 0 and 1. We're just going to be using UART 0, since 1 isn't really connected to anything that I can use for a USB. All right, I talked about some standard baud rates. Back when I was your age, baud rates of 300 were the norm. In the when I first started teaching, I had a 2400 baud modem, which I think I spent $600 on, and I used that to stay at home and do email from home and things like that. And it was pretty cool. In the days when faculty were actually allowed to take gifts from students, I had a student who had graduated a year or so ago. He came to visit me one day, and he brought me a modem that worked at 19.2K down here. And he said this tested, he was working for a modem company. He said this tested with problems on the assembly line and was rejected. It was going to be trashed. I grabbed it. I thought you might like it. I said, you're absolutely right, I would. And it did in fact work, and I used it for several years. That was a 19.2 baud modem. Again, still incredibly slow compared with typical cable download speeds of, I don't know, anything between 5 and 50 megabits per second. 19.2K doesn't sound that fast, but years ago it was. If you are doing streaming video, high baud rates are pretty important. If you were just sending some status information from one device to a computer, 9600 baud or even 2400 baud is probably fast enough, far faster than it needs to be. So we're going to look at using.
So how does things like video streaming, how does it pull that off? Just a really high baud rate, or is there a different protocol happening?
Well, with video streaming, there's actually 2 things going on. It's a really high baud rate. I would guess all of you are in the range of probably 2 to 4 megabits per second if you're seeing my video and audio. There's also a lot of, there's tons of research in terms of video compression. And the way that works, if you look at the frame where I'm talking, the only thing that's really changing is my mouth. And all the background, which is actually a pretty detailed background, that's all static, and hence the video compression is such that it doesn't have to transmit that each time. It's just transmitting the pixels that are changing. And there's been a ton of research over the last many years. And obviously people like Netflix and Hulu and other streaming video services have taken a lot of advantage of that. So A, it's a very high baud rate, and B, video compression is a really big thing these days. There are different delay factors that go into this 16-bit register here, or 2 8-bit registers. Really only 12 bits are used, but we allocate 16 bits for it. And let's see, we're just going to look at, okay, calculating a baud rate. If you know the baud rate and you can calculate what goes into the baud rate register. If you know it's in the baud rate register, you can calculate the baud rate. We talked a little bit about percent error last time. If I go to the data sheet, yeah, okay. In the data sheet here, hopefully you can see the data sheet now. There are tables, and if you have a crystal oscillator frequency of 1 megahertz, these are the delay factors. If you want to do 2400, you put a delay factor of 25. If you have a crystal of 2 megahertz, you can put a delay factor of 51 in to get a baud rate of 2400. You go through the several here. You come up to a 16 megahertz crystal. And last time we decided that 103 was a good, by means of calculation, 103 was a delay factor for 9600 baud. That's got a percent error of about 0.2%. You're actually transmitting, I think we figured at 9615 baud. If both devices happen to be 328 PBs and they both have a delay of 103, they're both going to be off by 0.2% in the same direction. So it's going to be a perfect match. If, on the other hand, you were communicating with some other piece of equipment, then every 1,000 characters or something like that, you might have to intentionally put in some idle time so they could sync up with one another again. We also saw there were some crystal frequencies that produced 0% error. I mean, without looking at this table, you might ask, why would anybody ever want to get a crystal frequency of 18.4320 megahertz? Okay, well, the answer is because look at the percent error up until 250K, 0% error. And that is just happens at the delay time, and that particular crystal frequency is perfect for doing baud rates. And that's probably why it exists.
So how much error can there be before there's problems? Like, is some infinitesimal amount of error acceptable?
It depends on how long you're going to stream without going to idle. So if there's 0.2% error, and I can't do this off the top of my head, but if you were to stream 1 million characters, one right after the other, so you've got one stop bit, and then a start bit, and then a character, stop bit, start bit, and another character. Rather than testing the high or the low in the middle of each character, in the middle of each bit, it's going to begin to drift a little bit. So it gets closer and closer and closer to one edge. Eventually, it will be looking at, well, looking for a start bit, and it will still be on the stop bit or something like that. That's the point where there's going to be a problem. How many characters that is, you'd have to look at how many characters with 0.2% error before I'm off by more than 1/9600th of a second. And it probably less than roughly 10,000, probably 5,000 characters would be my gut feeling.
And someone was asking about negative percent error. What does that mean?
The negative percent means it's just off in the other direction. This calculation is probably 416.2 or something like that. So rather than, ideally you've got a square wave like this, a square pulse. And ideally you're checking right in the center of that pulse to see whether it's high or low. In the case of, and this, I may have this backwards, but in the case of a positive error discrepancy, you're moving this way. In the case of a negative error discrepancy, you're moving that way. And eventually you're going to not be in the proper bit at all. You're either going to be in the bit before or the bit after. And that's the point where you get bad information. So my gut feeling is if it was 0.1 at roughly 10,000 baud, you could probably do 1,000 characters. Yeah, you could do 1,000 characters before you had a problem. If it's 0.2%, you can probably do about 500 characters before there's an error. In order to avoid that, every 400 characters as you're transmitting, you would need to just put a delay of a millisecond when you didn't transmit anything. And then it would, the receiver would read that as an idle time. And then when you did the start bit again, it would be back in sync exactly. Now, probably if you're doing high-speed data transmission between a 328 PB and some other device, you probably want to use a crystal frequency in the neighborhood of 18.4320 megahertz or something like that. One of the crystal frequencies that produces no error. And it depends. If this was a medical device, absolutely that's what I'd want to do. If this is controlling a light board, you probably aren't going to be sending characters that frequently anyway, so you wouldn't care. All right. Let's go back to this. So you can calculate a baud rate delay, or you can look it up in a table. All right, talks about percent error there. Looked at. I just showed you the table out of the data sheet. Okay, the couple of pins of interest, PD0, PD1, are the receive and transmit for UART0. There's also these pins, which really aren't connected to anything that goes to a USB type of a connection. You could connect these pins to a MAX 232 and communicate with some external device. Right now, I alluded to this last time. I think if you are looking at this diagram in the book, the arrows are in the wrong direction. The red arrows are correct. At some point, I have an 8-bit character. I need to add information to the beginning of it, a start bit, add information to the end of it, a stop bit, stick that into a shift register, and it's going to get shifted out 1 bit at a time. All of that hardware exists, and you don't have to worry about shifting it out 1 bit at a time and controlling what the timing delay is and stuff like that. This UART is a piece of hardware inside the 328 PB, and it will take care of all the timing for you. To transmit a character, you will write an 8-bit character. For the purposes of this discussion, let's say we're always doing 8-bit characters, even though we can do 5, 6, 7, 8, or 9. Look, we're going to put an 8-bit character into this particular word and we write it. It will then, the hardware all on its own, will put that character into the transmit data buffer register. And it will then, first time anyway, immediately put it into the transmit shift register. These operations take maybe 130 nanoseconds, two clock cycles. So you write a character to this register, and the next clock cycle, it puts it into the transmit buffer. The next clock cycle, it would put it into the shift register. So 130 nanoseconds. Now a baud rate of 9600 is roughly 1 over 10,000. And that, I think, if my math is good, is about 10 microseconds. So to shift out 1 bit takes 10 microseconds. To shift out 10 data bits, or 10 bits, the 8 data bits plus the start plus the stop, takes 100 microseconds or 0.1 milliseconds. So to shift this out is going to take 0.1 milliseconds. So suppose I want to transmit a phrase like Star Trek lives. Okay, I take the S, I write it, It goes into this buffer, it goes into the transmit shift buffer, and it begins to transmit out the first bit. While it's transmitting the first bit, I write the T into this transmit buffer, or into the UR data register, rather. It immediately puts it into the transmit buffer. Now, so far, 3 times 62.5 nanoseconds have elapsed, maybe as much as, say, 6 times 62.5 nanoseconds have elapsed. I'm still in the process of transmitting the first start bit of the first character out of the transmit shift register. So the T is sitting in this data buffer. The S is sitting in this shift register being shifted out. First start bit has been shifted, is in the process of being shifted out. What happens when I write A, STA is in Star Trek? I write the A here, which if I put it in here, I've destroyed the T. If I try to push the T through, I've destroyed the S. There is a very limited amount of data that the hardware can buffer. It is up to you as the programmer to look at some flags, or interrupts can be used as well, to see if there is a character in this transmit buffer before you write the next character into the transmit buffer. Okay. You can put characters into these registers or into this transmit register much, much faster than you can transmit it. That's the bottom line. On the receive side, when there is a piece of data in the receive buffer, you at some point need to read it. While you are messing around doing other stuff, a character in this receive buffer could be overwritten because another character is received. That's going to take a long time, but let's say some data is coming in, A, B, C. Okay, the first start bit of the A comes in, then the data bits come in, then the stop bit comes in, and there is a character received, the A. As soon as the character is received, it is put into this receive data buffer automatically by the hardware. And then the next character coming in can get shifted into this receive register, receive shift register. It is up to you, the programmer, to retrieve the character out of this receive data buffer before the next character is received. Now at 9600 baud, you've got roughly 0.1 milliseconds, long time, and sometime in that 0.1 milliseconds, your program is going to come and read this receive data buffer register. There is a flag that's set every time there is a new valid character in this receive data buffer register. So periodically, you've either got to check that flag, or you can set it such that an interrupt is generated, and in the interrupt service routine, you read this register. If you don't do that, and another character is received, then it writes it on top of this unread character, and at that point, there isn't what's called an overrun error, and there's a flag that's set that can be tied to an interrupt as well. Overrun error, and you need to somehow do some error control or error processing to figure out what to do. It may be as simple as sending some characters and say to the other device, you've got to resend some data. I screwed up, send some data. Or maybe you can ignore it, but that's for the programmer to decide. All right.
So it only does one by every microseconds.
I'm sorry, say again, AJ?
So it only does 1 byte every 10 microseconds. Could you do an interrupt to see when it's done writing?
Okay, we're talking about receiving or transmitting.
Transmit it.
Okay, when this, okay, when I finish transmitting a character out, if there is a character in this buffer register, it is automatically shifted into the shift register. Automatically, I'm loaded into the shift register is a better choice of words. And there is a flag that's set saying the transmit data buffer register is empty. So I could either pull that flag or I could tie it to an interrupt. And then if I've got an array in C, which we're actually, don't know if we look at that today or next time, but if I've got an array in C, I could take the next character out of that array, write it to the transmit data buffer register. So the processor will set a flag and optionally generate an interrupt each time the contents of this data buffer register are loaded into the shift register. Whenever the last bit is shifted out of the shift register, it automatically will take what's in this transmit data buffer register and load it into the shift register, which gives you kind of a 1 byte buffer. All right, there are a lot of stuff in here that's not really important to remember, but when you write to the UDR register, again, writing UDR 0 has a different set of bits that are read from than are written to. So I write to the register, eventually it gets shifted into the shift register. There's all kinds of parity that can get generated. The pin control, go again, go ahead again.
When you were explaining some of the stuff, I think your audio cut out because I didn't hear anything. And you
Okay,
were
all right, let me start again here. Okay, when I write to UDR 0, UR data register 0, I write to a different set of bits than if I read from the UR data register 0. I frankly wish they'd name this 2 different things, but it's a different location you write to than read from. And this diagram kind of shows that. And one of these arrows is in the wrong direction. Yeah, this should, I'm going to change it live here. Oops. Reading should certainly, okay, and I'll save that. Okay. All right. So so when I read, I am, just reading from a different set of bits than when I write. Go back to my laser pointer. Okay. When I write a character to UDR 0, it goes into this transmit buffer. When this shift register is empty, it will automatically load what's in the buffer to the shift register. If parity needs to be generated, it gets added in here. Pin control adds the start bit and the stop bit. And then it gets sent to the output pin. In the case of reading, the circuitry in here that will take off the start bit and the stop bit, check the parity, and then put it into the shift register a bit at a time. And then when a full 8 bits, if we're doing 8 bits, is received, it automatically gets loaded into this receive data register, where I can then read it by saying either X equals UDR 0, or in the case of assembly, in UDR 0. All right. I think that's pretty much the same thing. Oh, except now we're kind of looking at data sheets. This is taken directly out of the data sheet. I think this is out of, just go ahead a bit here. If we don't, all right. I think that I'm pretty sure this is out of UART Control and Status Register A. There is a bit, most significant bit, that says there is unread data in this receive buffer. So a character has been received, shifted in bit by bit. Character is complete. It is automatically loaded into this receive buffer, UDR0, when we read it. And this particular flag, RXC0, I believe it's in the, well, we'll look at that on the data sheet in a minute. I believe it's in UART Control Status Register A. It says there is data in the receive buffer that you have not read. So it is important that before another character is received, that you read what's in here. Okay. The next piece is the complement flag, transmit complete. Okay. And you're going to look at what this says. It's set when the frame in the transmit shift register has been shifted out and there's no new data present in the transmit buffer. So in other words, when that happens, it is time to load another byte into this transmit register. All right.
So I could see an implementation with this where you have all the characters in an array and then you have an ISR to just load the next one in when the interrupt goes.
That is exactly right. I should actually go back and clarify this previous one just a second here. Look at it. Because I know
Oh,
I don't
also
have,
your video's not really, like your webcam's not really.
Yeah, if you can hear me, I occasionally get a message saying your internet is unreliable. I'm not sure if that's my internet or if that's just the internet in general.
Working. A little column A, a little column B.
What I'm gonna do, let me, I don't know if it will make any difference or not, but, all right, I'm just gonna turn off the fancy background and that may help the video bandwidth a little bit, I don't know. With what I just said about video compression, I don't think that will make much difference, but it can't hurt anyway. Okay, this, there's actually two different flags relative to the transmit side. With the receive side, if I go back, okay. If I go back to the receiver, you don't really care what's happening in here. All you care about is when there's a character in the receive buffer I've got to read. With the transmit side, you might care when this is empty and if there's no character here. I'm not sure who said it was an implementation would be to have characters in an array when you get an interrupt service routine saying this is empty. Output the next character. That works really well in the steady state. But supposing there are no more characters to output, supposing you've printed everything you want to print. This transmit shift register has just been emptied and there's no data waiting in this data buffer, this transmit data buffer. what do you do then? Well,
I could,
that happens. So you've shifted out the last character. There's no character waiting to be transmitted. What you would need to do is, or this flag gets set, transmit complete, and you need to basically stop the interrupt from occurring. So you're going to set it such that an interrupt doesn't occur all the time now, because otherwise you'll be just transmitting nothing, and that's not what you want to do. So when this flag is set, and it can be tied to an interrupt, you want to basically stop this interrupt from occurring each time a character is done. And I've got code that we're going to look at probably Friday now that we're going to look at and how to exactly do that. The other piece, when you are in the process of transmitting a character, let's see, process of transmitting, finish transmitting, there's a character in the data buffer. So I finish transmitting a character, the character in the buffer is loaded into the shift register. I can now throw another character in here. When that condition happens, so I've just loaded something from the transmit data buffer into the shift register, I can then, or then this data register empty flag is set. In other words, it's time to store a new character in this register because the one that was just in there is now being transmitted.
so when you put something in the transmit shift register, does it automatically get pushed out to the pin, or is that a separate?
Okay. You never put something directly into the transmit shift register.
Well, into the buffer.
Right to the transmit data buffer. And if there's something in this register, if you've written something into this register, when the previous character is shifted out, the hardware will automatically load what's in the transmit data buffer register into the shift register. And then it sets this flag, data register empty, which you can either poll or tie to an interrupt. And it's up to your probably interrupt service routine to put the next character to be transmitted into this. Now, if you tie this to an interrupt, probably before the first bit of this character in the shift register is shifted out, you will have loaded the next character to be transmitted into the data buffer register or into UDR0. Again, so, and if you think this is difficult to understand, think about the poor slobs that had to design the hardware. Some truly impressive stuff that they did. All right, I think we, okay. This is in, I think that I'm pretty sure this is in, oh yeah, let me, hide floating meeting controls. Okay, yeah. This is in status register A. Okay, this is right out of the data sheet that receive complete, transmit complete, data register empty. And then there's a few other bits that framing error. This is, note this is a read-only bit. If somehow things get out of sync, actually let me check here. Yeah, basically is if it doesn't get a stop bit when it thinks it should, then you have a framing error. Data overrun error says you haven't cleared out the receive buffer prior to another character being loaded there. This is a parity error flag. I don't know if okay, so this is a parity error flag. If you're using parity and there's a parity error, that bit gets set. This is a double the speed, double transmission speed. I think this is kind of a holdover from the early days when clock frequencies were relatively slow. If you had a 1 megahertz clock, that was considered pretty fast. And sometimes just to get baud rates of like 4800, 9600, you had to sort of do a doubling on clock speed. For anything that I think you will ever do, or I think anybody will ever do, leaving this at 0, just doing normal transmit rate will be fine. This will also allow multiple processors to kind of connect together in a ring using UARTs. And for our purposes, we're always going to leave that as a 0. We're not doing multi-processors kind of stuff.
So how do you actually go about reading information in? Like, I get what you do with the memory, but how would you read something in from the USB?
Okay, I don't know. Okay, we're not going to get to it today, but if you go ahead on the slides here, we're going to set something up there. Somewhere I've got some code. Okay. This isn't actually reading something in, but this is sending something. There are some registers set up here. And again, this code is on the M drive. Oh, sorry, these slides are on the M drive. You can type this code in. So this is setting stuff up. It should look very familiar to the way we set up control status registers on the timers. The baud rate register I set to 416, which is a 2400 baud rate. And then all I did here is I looked at the flag, the data register empty flag. And as long as that flag was 0, I just continue to spin in this while loop. When that flag becomes 1, meaning the data register is empty, and I can send another character, I write the character A to the data register. All right, if we go ahead a little bit, I put the analog discovery on here, looked at the bit times, and came up with 417.1 seconds. 1 over 2400 is 416.7 seconds. That's, I think, within our margin of error. So the bit time looks good. And then I looked at the data stream. Again, we'll look at these slides more next time, but just to kind of get to where we are. Right. To use a program like PuTTY, which can be used to do SSH kind of stuff or plain old terminal stuff.
Your audio is cutting out.
Okay, my audio. Yeah, okay. I'll repeat it. I don't know what to do about the audio cutting out at this point. I think the internet may be breaking. I will certainly do speed tests on my machine and see whether it's my connection or not before next time. To connect PuTTY to your board, if you don't have PuTTY, by the way, it's a free download. Just type in PuTTY to Google or DuckDuckGo and you'll see a website that you can download it from. You need to go to Device Manager. So as I say here, type Device Manager in the search box if you've never used it. Under ports, you will see the ME debug virtual COM port and some number COM something. It could be COM 24, it could be COM 2. But whatever that is, you would then, when you run PuTTY, type in COM4 on whatever serial. First, you're going to click serial. Then you have an option to specify which serial port. If you are doing something other than 8 data bits, 1 stop, no parity, you need to click serial here and adjust it for what you're doing. You can save a particular setup if you want to, just by clicking save, and the next time it's a lot faster. Note, I've saved a few different, I think a 328 PB for 9600 328 PB for 300. I think I saved and got some others. And yeah, if you do something other than the default, you can set something up. And then if you were to say, okay, you get a terminal screen. And in the case of the program that I just looked at, we get a bunch of A's, which are going to continue forever. We're gonna
It's like my social media feed.
It's what? Okay. All right. Next program, and again, we'll pick up here next time, but next program, suppose I want to send out a string. And I do some different things, 300 baud. And this time we're going to use interrupts. That's where it really gets interesting. Okay, in terms of lab, I guess next week's lab, since by Friday, I'm not going to cover enough stuff so you can do UART stuff. The lab for this Friday and next Monday is going to be a repeat of the previous week. I know we're slipping behind, but we're doing the best I can, or I'm doing the best I can. I know there are still a couple of you that don't have boards. I'm waiting for 7-segment displays to come in, which are on their way. As soon as I get those 7-segment displays, then I can mail stuff out. I think there's 6 people that are waiting on boards, and I will get those out as soon as I get the 7-segment displays. Okay, any questions? Okay, I will see you on Friday then. Enjoy.
All right. See you Friday. Thank you.
My wife says, stay safe and wash your hands. She's a nurse. So
You too, Professor.
blessings all. Okay, bye.
All right. Be safe. Bye.